Welcome to Maths with EJD. In this video, like I promised, I'll be talking about the power series method. Of course, that's one of the method we can refer to as series solution methods, series solution methods for ODEs. Okay, so and there are two of them. We have the power series method, and then we have Frobenius method, which we'll be looking at in the next video. Frobenius method. And like we learned already, for power series method, we are looking for a series of ANs, whereas for Frobenius, we are looking for R and series of ANs. Okay, so here we have just recurrence relation from where we get the ANs, whereas from for Frobenius method, we have indicial equation. That's where we get our R's from. Yeah, indicial equation. Okay, and we have recurrence relation from where we get our ANs. Okay, that's the key difference, recurrence relations. Another difference is that power series method is used for problem that have um, ordinary points, and Frobenius method is used for problems that have what we call regular singular points. Okay, so yeah, our focus now turns to the power series method. Let's see that power series method. In the last video, I already gave a kind of brief on the two of them, but here we want to actually take an example and look at it very thoroughly. So the power series method is a technique used to solve linear differential equations, particularly when the solution cannot be expressed in elementary functions, or what you can call closed form. Okay. Uh, it expresses the solution as an infinite series expansion, as an infinite series expansion. The method is most commonly applied to linear ordinary differential equations around a point often referred to as the ordinary point. So often referred to as the ordinary point. And it is usually, the ordinary point is usually x equals 0, but any point, any point can be chosen. Any point can be chosen. Okay. All right. So let's talk about let's switch gear and talk about mm, steps for using the power series. So we have steps for using the power series method. So of course, it's not the first time, right? The first step is you assume a power series solution. That is the essence. You assume a power series solution, just like in the case of what we call the Um, I'm trying to remember characteristic equation method. When we solve a homogeneous equation, right? You assume that the solution is y equals e raised to power rx, and if you substitute that, you can get the characteristic equation, which you solve to find the powers, to find the values of R. Okay. So here you assume a power series solution. So for a differential equation, assume the solution y of x is the form of a power series, and that is yx equals summation from n equals 0 to infinity of an, actually x minus x naught raised to power n. But since usually x naught is 0, then we can just say x raised to power n like this. So this is the assumed solution for the problem. And then after that, we go for step 2, where we talk about where we substitute. So here you substitute into the given differential equation. Okay, so substitute this assumed solution now into the given differential equation. So now you substitute the series form of y of x and its derivative into the differential equation. If the equation involves higher derivatives, calculate the derivative of the series term by term. So usually, since you are solving differential equations, at least you're going to have one derivative. So in that case, you need y prime of x, right? So you're going to have y prime of x based on what you have up there, and each time that happens, you have a shift by one by in the value of n, you have it by one. Instead of starting from 0, you have n equals 1 to infinity now. And when you differentiate that, you have n an x raised to power n minus 1, like that. That is y prime of x. So if you also have second derivative, you have y prime prime of x to now be summation from n equals 2 now, because you have differentiated the second time. So you have that into you now have n equals to infinity of an, or if you like, n into n minus 1, an x raised by n minus 2. So that is how you have this, the second derivative. So you can continue if you have third derivative and so on and so forth. Okay. So the next thing you want to do after these two steps would be step 3, where you simplify and collect terms. Simplify and collect terms. So you simplify and collect like terms. So after substitution, simplify the resulting equation and collect terms by powers of x. Okay, by powers of x. Then number 4, you can then find recurrence relations. Find recurrence relations. So you find recurrence relations. Okay. So equating coefficients of like powers of x. Uh, Okay, I guess okay, I mean, I've not been writing. Let me just say it. So equating the coefficient of like powers of x gives a recurrence relation for the coefficients n, okay? Coefficient an. So the recurrence relation allows you to find the coefficients in terms, okay, I guess I want to write this. Um, the recurrence relation, the recurrence relation allows you to find the coefficients. That's like the key thing you're even doing. Allows you to find the coefficients in terms of the initial values. Typically, A naught and A1. So it means you're going to be given the start, you have some kind of starting values, A naught and A1, which you substitute to get what you need to get the other values of from A2 upwards. Then you have step, I think 4, I believe it's 4 now, okay? Or even 5. Okay, this is 5 now. So in 5, we now solve for coefficients. Solve for coefficients. Okay. So in solving for coefficients, so you solve the recurrence relation, solve the recurrence relation to find the coefficients an. Okay. Of course, with that done, then we can move on and talk about something else. So let's talk about, let's do an example, something really elaborate. solving a second order linear ODE. So consider the following second order linear differential equations. Differential equation rather. Differential equation, which is y prime prime of x minus x y prime of x minus y of x equals 0. Okay. Now, one reason why you would use series solution why you need series solution is because of this coefficient x. So it's a variable coefficient. If you have constant coefficient, then normally you go ahead and use characteristic equation and do all the things you have to do. But in this case, you have a variable coefficient of one of the terms. So in that case, you're going to need series solution, and then you have to consider, is it an ordinary point or a singular point and things like that. But of course, since you are dealing with so since you are dealing with power series method, automatically, and we have seen in the preamble also that x in this situation is an ordinary point where x is equal to x naught. So here now we go for the steps. We go for the first step. Step one, assume assume a power series solution, like we said before. Assume a power series solution first thing. So you assume the solution is of the form y of x equals summation from n equals 0 to infinity of an x raised to power n. All right, we have this first. And then from the equation, right, you have y of x already. So you need y prime and you need y prime prime. Okay, you need y prime prime. So you need to get all those two derivatives. So y prime of x would just be summation from n equals 1 to infinity of an x raised to power n minus 1. That's the first one. And the second one, you need y prime prime, second derivative. Y prime prime of x now would be summation from n equals 1 to infinity. You have your you have n into n minus 1, x raised to power n minus 2, like that. And then you have the second one. So you solve you're assuming the power series solution, and of course you need the derivatives. Then in step two, you can substitute. So substitute into the differential equation. Okay, so substitute the expressions for y of x, y prime of x, and y prime prime of x into the equation. So the equation we have is y prime prime of x minus x y prime of x minus y of x equals 0. Okay, so if you substitute all of that into it, then you get summation from n equals 2 to infinity of n into n minus 1, x raised to n minus 2 minus x y prime, right? And y prime is summation from n equals 1, this is 2, n equals 1 to infinity, an into n x raised by n minus 1. And lastly, you have y of x itself, which is summation from n equals 0 to infinity of an x raised by n. All of this now is equal to 0. That's the second step, okay? With that second step done, you move on to the third step. That's step 3, where you simplify. So simplify the equation. Simplify the equation. And when you simplify, so here I think this is necessary there, right? We can shift indices. So you can see one is starting from 2, the other is starting from 1, and one is starting from 0. We can shift all of them. So we can shift indices to make all terms have the same power of x. Okay. So for the first term, shift the index n by 2. Okay, we shift the index n by 2. That means summation n equals 2, which is the first term, to infinity of n into n minus 1, x raised to power n minus 2, becomes summation from n equals 0 to infinity. So we are shifting it 2 steps backwards, and if that happens, it means that we are going to have an plus 2, like an gains 2 steps, and then every other term gains two steps too. So n becomes n plus 1 and then plus 1. That's n plus 2. And n minus 1 becomes n minus 1 plus 1, which is n plus another one. That's n plus 1. Okay. And then we can now adjust x raised to power n minus 2 to x raised to power n. So now we have x raised to power n while adjusting all the other terms, as we can see there. So that is the second term right there. Uh, okay. So this is the second term adjusted now. This is the second term adjusted. Then that's for the first term, right? For the second term, so you see the second term has a value of x here, and we need to shift this one by one step. So let's see how that goes methodically. That's for the second term, right? Uh so I say for the second term, okay, we have, that is minus x into that's minus x into y prime of x, right? So there we have minus x summation n equals 1 to infinity an n x raised by n minus 1. So if you work this well, you have minus. So the x goes inside to bring the power of x down to normal. So first of all, we can do that. So we have minus summation from n equals 1 to infinity an n x raised power n. So this x alone normalizes n equal n minus 1. But here, uh, here we are going to, we still have n starting from 1. So we need to shift it by one step. And if we shift it by one step, it means we have minus summation from n equals 0 to infinity, right? To infinity of, instead of an, and because it's gaining one step, we have an plus 1, and n alone becomes n plus 1. Then we have x raised by n plus 1 also. So because of the value that was already decided before. So second term becomes like this. Okay. What else? Okay, I could just say minus x y prime of x now becomes this, so I can circle that. All right. So we have that. Now, the third term remains the same, right? Because it has power x raised power n already. Okay. So we don't want anything having negative power. I think that's basically the deal here. So now the third sum remains the same. Remains minus x from n summation from minus summation from n equals 0 to infinity of an x raised power n. So that remains the same. So thus the equation becomes the equation becomes we can now put everything together because everything is now starting from 0. So the whole thing now becomes summation from n equals 0 to infinity of, let me just do it this way, an plus 2 into n plus 2, okay, into n plus 1. Xn plus 1 is now common, except for, uh, mm, let me see, for that second term, if you want it to be xn plus 1, right? Um, Where's that? Okay, we have an plus 1. It looks like we need to maintain an x for that one, right? So we have an plus 2, n plus 2, n plus 1, minus the other term, which is now an plus 1, n plus 1. If you're going to have x n outside, this one has to keep a value of x. Okay, that's what I think, actually. That's what I think. So this should actually be, this is minus an plus 1, n plus 1, x minus an, okay, into x raised power n, so that everything will now be equal to 0 because everything is starting from 0 to infinity now. So this is important. So this is the whole thing together. After we shifted all the steps, then we go for step 4, which is where we now solve we solve for the recurrence relation. Solve for the recurrence relation. So to solve for the recurrence relation, you say for the series, okay, I guess I need to write for the series to equal 0 for all x, the coefficient of x must, the coefficient of x must be 0. Okay. So therefore, for each n, we have the recurrence relation. We have the recurrence relation. Okay, an plus 2, n plus 2, n plus 1. All of that should be equal to 0. So we have an plus 2 into n plus 2 into n plus 1. All right. The coefficient alone. What that simply means is that this whole thing should be equal to 0. If that must be equal to 0, right? But I mean, I have an issue with this x that is still here right now. So it looks like the whole thing has been lumped together. Um, do we just ignore that or leave it the way it is? That's the concern I have right now. Okay, let's see what happens. So this is an plus 2 into n plus 2 into n plus 1 minus an plus 1. So all the coefficients put together, right? Minus an, all of this should be equal to 0. Now you see that I've skipped that x. I don't know what to do with that x right now. So let's see what happens. Okay. So for, but basically for this to be equal to 0, then we need to equate all these coefficients to 0. So that simply means now that we have an plus 2 into n plus 2 into n plus 1 equals an plus 1 into n plus 1 plus an. Okay, that's what we should have. And in that case, now we can make an plus 2 the subject. So we have an plus 2 equals an plus 1, n plus 1, all right, plus an divided by n plus 1, n plus 2, as you can see up there. So with this in place now, so this becomes like an expression we can always use. All right. So in step 5 now we can solve for the coefficients. Step 5, so solve for coefficients. Solve for coefficients, and basically what we need before are the ANs, right? Now we can find the coefficients. Now we can find the coefficients. We can find the coefficients an recursively, because we have a recursive formula for that already. Recursively starting with initial values, starting with initial values, a naught and a1. All right. So for example, okay, let me just go. For example, if a naught is equal to 1 and a1 is equal to 0, I mean, we can have that given us, or we can just choose randomly. So if you take a naught to be 1 and a1 to be 0, then we can compute. We can compute the following. We can compute that you know uh, A2 based on this expression, right? Well, let me just even write it out. So we know already that we have an plus 2 equals an plus 1 into n plus 1 plus an all over n plus 1 into n plus 2. Okay, so let's, at n equals 0, for instance, we know that a2 is equal to, a2 will be equal to, when we are taking n to be 0, so that'll be a1 into a1 into n is 0, right? A1 into 1 for sure. All right, plus a0, okay, because n is 0, all over 1. So this is like a1 into 1, of course, into 1 times 2, okay? So that will be A1 plus A naught all over 2, basically. So A1 is 0, A1 is 1, all over 2. So it means that A2 is simply 1 over 2. So we have A2 that way. And then we can have the other one. We can go for A3. So A3 now is simply, that means n is equal to 1, all right? N is equal to 1. So if n is 1, so it means from this now, n is 1. So 1 plus 2, that's why we have A3. So an plus 1, that is A2. That'll be A2 into n plus 1. That is 1 plus 1, that's 2. Then plus A1, all right? All over 1 plus 2, 3. I mean, 1 plus 1, 2. That's n plus 1. Then 1 plus 2 is 3. And then we have 2A2 plus A1 all over 6, basically. And then this is 2A2. We know A2 is half. And then A1, we know that to be 0 all over 6. So 2 cancels 2. So A3 is simply 1 over 6. A3 is 1 over 6. We have that. Then we go for A4. So A4 now means n is 2. Maybe I should write this to make it clear. So for n equals 0, this is what we get. So now for n equals 1, this is what we get. So now for n equals 2, so it means that A4 would now be, so 2 plus, an plus 2 is A2 plus 2, that's A4 equals A3 into 2 plus 1, 3, plus A2 all over n plus 1. That is 2 plus 1, 3, then 2 plus 2, 4. So this is 3A3, 3A3 plus A2, 3A3 plus A2 all over 12, okay? So that A4 now is equal to 3. The A3 we got before was 1 over 6, so this is 1 over 6 plus A2. We got A2 to be half, okay? A2 is half all over 12. So we need to take care of all this. So A4 is 3 times 1 over 6 is half. So half plus half all over 12. So half plus half is 1 all over 12. So it looks like we even have a pattern. So this is 1 over 2, uh, you know, the next is 2 times 3, 6. The next is 2 times 3 times 3. It looks like we have a pattern. But I mean, overall now we have A4 is 1 over 12. So we can continue like that. All right. So we continue. So we can go on until we get AN, whatever that is. So we just keep on to whatever terms we want. So after all of this, now we can go for the conclusion. So in conclusion, okay, the solution the solution to the differential equation, if you remember where we started from, the solution to the differential equation, all right, the solution is the solution to the differential equation, so just a minute. Okay, so we see that the solution to the differential equation given by the power series, okay, is y of x, which is equal to summation from n equals 0 to infinity an x raised to power n, okay? And that means we have y of x to be equal to, starting from 0, so we have a0 x raised to power 0 plus a1 x raised to power 1 plus a2 x raised to power 2. You know, we have up to a4, right? So let me expand it up to a4. So we have a4, sorry, I'm jumping mega together. So a3 x raised to power 3 plus a4, you know, x raised to power 4, and that goes on like that. So we can fix this value. So y of x is equal to a naught. We took a naught to be 1. X raised to power 0 is also 1. A1, we took it to be 0, and we have x raised to power 1 plus A2, I think that was half x squared, plus A3, that was 1 over 6 x cubed. A4, that was 1 over 12 x raised to power 4, plus all of this. So that finally we have y of x is equal to 1 plus, this is 0, so 1 plus half x squared plus 1 over 6 x cubed plus 1 over 12 x raised to power 4. So now this is the solution to that differential equation we have. So it's a series solution because the problem itself has an ordinary point at x equals 0. Okay, so we have a series. So this is the first, so we have a series solution for the problem we had to deal with. Okay, um, I know it's a bit tedious, but you just have to be careful. You just have to follow mindfully, and you'll be good. Let's go for some kind of practice, so you can try your hands on some questions. So let's practice with the following questions. Um, so I'll just say solve the following as usual. The following. Solve the following. Okay. Question 1, you have y prime prime plus xy equals 0. Okay. Then also number 2, assume a power series solution for the equation below and find the first four terms of the series expansion. In our case, we also find the first four terms, 1, 2, 3, 4. Okay. Find the first four terms. So you can just always find the first four terms, even if you're not told. So you have y prime prime minus xy prime minus 2y equals 0. Number 3, solve the following differential equation using the power series expansion around x equals 0, because that's just like what we did. So that's 1 minus x y prime prime minus xy prime plus y equals 0. So this is going to throw some interesting dimension to your expansion by the time you are shifting powers. Then number four, what about you have y prime prime plus 1 plus x y equals 0. Okay. Question 5. Do we still have question 5? Yeah, question 5, you have y prime prime plus 2x y prime plus y equals 0. Okay. Then let's see, do we have more? Yeah. Interesting, we have more. Question 6, do x squared y prime prime plus x y prime minus y equals 0. So I think the tricky part is how to, when you begin to shift the powers starting from 0, right? Shift the value of n to start from 0. Then uh this one also says, okay, I mean, it's the same thing. Then solve the Bessel's equation. I think we'll be talking about Bessel in a jiffy. So let me take it to 7. You have number 7, y prime prime minus x squared y prime plus 2y equals 0. So try all this. Let me see your answer in the comment section, either on YouTube or on Facebook. All right. Also, let me know in the comment section how helpful these videos are for you. I also like to know that problems you like me to solve or topics you like me to teach, just comment, let me know. I may be able to find time to get to them. Or I mean, but check the channel first. I have so many videos already. Maybe what you're looking for is already there, so feel free to have a very nice time. And of course, if you have subscribed, thank you for that. If you have not, you'll be missing a lot. So subscribe right away and hit the notification bell, everybody, so you can always get alerted each time a new video is released. And don't forget to like and share so that everybody can enjoy this great teaching. Till I come your way again, keep doing maths right. Bye.